Okay, let's dive into this. Welcome to the explainer. You know, we almost always treat water as the ultimate simplicity, right? It's just that transparent, tasteless backdrop to our daily lives. We drink it, we wash with it, we watch it fall from the sky, and we really don't give it a second thought. But it turns out that right beneath that quiet surface, H2O is actually an aggressive, shape-shifting chemical rebel. Today, we are absolutely shattering the illusion of simple water. We're going to explore the fascinating and honestly sometimes destructive physics and chemistry that dictate the absolute boundaries of our modern world.
So think about this for a second. Is the liquid that literally makes up 60% of our bodies actually a rule-breaking rebel? It's a pretty provocative question, isn't it? Well, in the super rigid world of physics, most substances follow a highly predictable path. But water just consistently flouts the standard rules of thermodynamics. It is hands down the most anomalous liquid in the universe. It acts as both this incredible biological engine for life and a relentless threat to our global infrastructure. So let's look at exactly how it breaks the rules, starting with its thermal boundaries.
Let's talk about the absolute ceiling, 100 degrees Celsius. Now, this isn't just a fun fact you memorized in grade school. It literally dictates the absolute boundaries of industrial phase change stability. At normal atmospheric pressure, 100 degrees is the thermal ceiling for steam generation. Every single high-pressure boiler, every steam turbine, every massive power station on Earth has to manage incredibly precise control systems around this exact boiling point just to keep our energy grid running. Which, by the way, is exactly what's powering the screen you're watching this explainer on right now.
Now, on the flip side of that, we have 0 degrees Celsius, and this threshold threatens global infrastructure in cold climates with absolutely catastrophic failures. Here's the thing. Unlike almost every other liquid that just shrinks as it freezes, water expands. This really unique expansion induces what engineers call hoop stress. Basically, it's extreme mechanical pressure that causes aggressive burst failures in metal piping. It's the exact reason a winter freeze poses such a massive threat to your home plumbing. It takes this huge industrial problem and scales it right down to a highly personal, incredibly messy nightmare.
Now, what's really interesting about this slide is that the most mind-bending anomaly happens right before freezing. Water actually hits its maximum density at exactly 4 degrees Celsius. As it cools from 4 degrees down to 0, it expands. It becomes less dense. This physical defiance means that solid ice floats right on top of liquid water. In the dead of winter, this creates this incredible insulating crystalline shield over lakes and oceans, which protects the aquatic ecosystems below from freezing solid. Honestly, if water followed the normal rules of physics, our oceans would freeze from the bottom up, completely turning our planet into a lifeless block of ice. No way we'd be here.
Moving on to Section 1, the universal solvent, an aggressive chemist.
So, we hear water called the universal solvent all the time, right? But this term actually reflects a literal inherent chemical greed. You see, water possesses a molecular structure that allows it to dismantle and dissolve a staggering variety of substances, way more than any other liquid. From salts and sugars to acids and alkalis, it just takes them apart. Now, in biology, this is fantastic. It acts as a high-speed transport system, aggressively dismantling nutrients to facilitate digestion. But out in the environment, this chemical greed means water is constantly acquiring chemical baggage. It acts like a shapeshifter, literally absorbing the world around it as it moves.
And this brilliantly illustrates just how aggressively destructive that solvent action can be. Just look at what happens when water interacts with certain metals, like sodium. It violently dismantles the metallic structure to produce metal hydroxides and highly flammable hydrogen gas. Boom! In the energy and manufacturing sectors, this inherent reactivity creates massive safety and structural corrosion risks. It's definitely not playing around.
And the craziest part? Water doesn't even need to touch the ground to start reacting. When it interacts with non-metal oxides up in the sky, things like carbon dioxide, it forms acids, specifically carbonic acid. What this means is that water is introducing early-stage acidification risks to exposed infrastructure before it even hits the soil. It is literally out there constantly forging entirely new substances mid-air.
That brings us to Section 2, the sourcing paradox, or the origin of chemical baggage.
Now, depending on where your water is sourced, its purity profile shifts dramatically. Let's break this down. First, you have rainwater, which is the purest natural source. It's naturally soft, but kind of acts like a giant sponge for atmospheric dust. Then you've got surface water, your rivers and lakes. These are highly vulnerable to terrestrial contaminants and industrial runoff, so they require a lot of filtration. But pay special attention to the irony of groundwater here. Sourced from deep wells and springs, groundwater is naturally filtered by the Earth's crust. That makes it microbially super clean. But here's the paradox. As it permeates the earth, the soil acts as a massive mineral enricher. The water absorbs high concentrations of heavy calcium and magnesium, making it the hardest and arguably the most industrially destructive natural water source we have.
Let's get into Section 3, the hardness problem, biology versus machinery.
So the crucial point here is what we call the paradox of purity. The exact same minerals, calcium and magnesium, that make groundwater absolutely essential for human bone and dental health act as a devastating threat to our mechanical systems. Seriously, what our bodies crave for nutrition and a richer taste actively wastes soap, acts as an insulating thermal barrier, and creates this really destructive scale that causes catastrophic failure in high-pressure boilers. Basically, what gives you strong bones will absolutely murder your water heater.
To manage this whole mess, engineers have to break down the taxonomy of water hardness into two distinct chemical camps. First up is temporary hardness. This one's caused by dissolved bicarbonates, and you can actually remove it by thermal intervention, just boiling it or by adding lime. Pretty straightforward. But then you have permanent hardness. This is caused by dissolved sulfates and chlorides. These salts are thermally stable, meaning you cannot just boil them away. No chance. They demand sophisticated industrial mitigation, like adding washing soda, running complex ion exchange methods, or going all out with full distillation.
Now, when you try to mitigate temporary hardness with thermal intervention, like boiling, it leaves something behind. It precipitates a solid byproduct called calcium carbonate, which we commonly know as scale. It's the exact same white, chalky crust you see building up inside your kitchen kettle over time. But on an industrial level, this scale forms a rock-solid mineral crust inside massive pipes and heat exchangers. It literally insulates the heating elements from the water, which forces these massive industrial systems to consume exponentially more energy just to reach their target temperatures. It's a massive, massive driver of operational inflation.
Which leads us to our final part, Section 4, a finite chemical resource, fighting back.
So how do we fight back against this rebellious liquid? Well, one of our most powerful tools is distillation. By forcing water through a multi-step phase change cycle from liquid to gas and then back to liquid again, you strip away absolutely all impurities and all forms of hardness. It is essentially the universal solution, but there's always a catch, right? It comes at an incredibly high energy cost. It's super effective, sure, but it is wildly expensive to run at a global scale. Let's move to and see how this builds into 3 really essential survival tactics beyond just distillation. First, we have pollution prevention. We absolutely must strictly eliminate refuse dumping. Solid waste leaches chemicals that become a permanent, totally integrated part of the water's chemical identity. Second, we need infrastructure conservation. That means aggressive leak repair and industrial wastewater recycling. And third, strategic dilution. This means mandating rainwater harvesting. By capturing naturally soft rainwater, industries can use it to dilute those mural-heavy hard water streams, which significantly reduces their chemical treatment costs. So, as you can see, protecting our infrastructure goes entirely hand in hand with environmental conservation.
There is a quote here that perfectly captures this entire threat. It says, "Because water is the universal solvent, its aggressive greed makes it exceptionally difficult to remediate once pollutants are dissolved into its chemical identity." This is absolutely crucial to understand. Contamination isn't just a bit of oil floating on the surface. Because of water's inherent chemical greed, pollutants fundamentally alter what the water is at a molecular level. Once it's compromised, the cost and effort of restoring it is often completely prohibitive.
Which leaves us right here. The very property that makes water so miraculous, its status as the universal solvent, is also its greatest vulnerability. It is the silent titan of our industrial revolution, and it's the biological engine of our bodies. So I want to leave you with this thought. Knowing what we know now, that water is a highly reactive, shape-shifting chemical rebel, are we truly doing enough to protect the universal solvent that keeps us and our modern world alive? Thanks for joining me for this explainer, and remember, keep questioning the simple things.